So this is going to be my video on data analysis and how you do all our labs for the entire year. And this video is actually going to be in two parts. This first video is going to be part one with linear data. And then later on, I'm going to have a video, which is part two, which is with nonlinear data. Okay. So here are the general steps you're going to be doing for all data analysis. Okay. And I'm going to be going over all of these steps, or how about this, as we do several examples, um, and as you do several labs over the course of the year, all of these steps will start to become quite familiar. And you'll start to see that every lab is going to be exactly these same steps. All right. So I'm going to go into more detail about some of these steps a little bit later. But for now, I'm going to focus on certain preliminary steps, the very first steps you need to be able to start with, right? Even before you do these things. All right. So the first thing you have to recognize is that every experiment has two variables. All right. So there's always going to be like a dependent variable and an independent variable. Like the most common example, say, of like certain experiment might be the two variables. Say if you were to like water a plant and you're going to adjust how much water you give it, and the thing you're going to measure is how much height there is. Okay, well, your two variables are clearly amount of water is one variable, and the height of the plant is another variable. And so the height of the plant would be dependent on how much water you give it, which is the independent variable. All right. So every experiment has two variables. All right. Um, if you know the underlying physics of an experiment, there is going to be a theoretical formula that relates to these two variables. All right. So there's always going to be some sort of formula that sort of governs how those two variables are related. All right. And from that formula, you should be able to do the following steps. So basically what I'm saying is every lab you're going to do this year, there's going to be some sort of equation, some sort of formula that relates the two variables in your experiment. All right. And then from this equation, you should be able to do these steps right here. Determine the y variable and the x variable, sometimes called dependent and independent variables. Right now, I'll just call it y variable and x variables. Right? And then when you determine those variables, you should be able to determine whether they're linear and linearize it if they're not linear. And then determine what the slope represents. All right. So I'm going to spend a lot of time. The main part of this video is just on these two steps right now. Okay. So let's focus on this step right here. Determine the y and x variables. So how to determine the y and x variables and whether they're linear. And you're going to base this off this theoretical equation that you had, right? Because I just told you right here that you should be able to, from the equation, determine this. So you're going to start off with the equation and determine this. So, all right. So you're going to have an equation and determine what the y variable and what the x variable is and whether they're linear. So let's just say you're doing an experiment with the two variables are p and t. And let's just say the scientific theory, the physics theory, or it doesn't have to be physics, or whatever, scientific theory says that those two variables are related by this equation. What you need to be able to sort of see is that I have now labeled the y and x variables. All right. And then I can see they're linear with each other. All right. Now let me break down how I knew which one was y, which was x, and how they were linear. Okay. First thing, you want to understand that all linear equations, you probably learned this in Algebra 1, that all linear equations, not all, but a common linear equation is to put in the form of y equals mx. Right? So most linear equations we like to write in the form of y equals mx. So you need to sort of look at this equation and sort of picture it as in the form of y equals mx, right? So one thing that's going to tell you right now is which one's the y variable, which one sort of is in the y variable place, and which letter is in the x variable place, right? So now you can already see between p and t that it seems pretty clear that p is the y variable and t is the x variable. Or I guess another way you can sort of think about it is that P depends on T. So T is an independent X variable and P is an independent Y variable. Right? So hopefully that way you can sort of see which one's the y variable, which one's the x variable. Right? And I put a kind of little box around it there. So like oftentimes, I kind of tell people to put a little box around their y variable, put a box around the x variable, stuff like that. All right. And then next thing you need to be able to sort of see is that they are linear with each other. All right. And the thing that I'm looking at that tells me that they are linear with each other is I'm looking to see what their exponent is. And if both of their exponents are 1, then they're linear with each other. Now here, there is no number there, but hopefully you guys remember that if there's no number, that means the exponent is 1. Now, because it feels like squared, you would see a 2 there. If it was cubed, you see a 3 there. Or if you see a square root or something like that, then you know it's not linear. Okay. So the fact that these two are right here have an exponent of 1 means they are linear with each other. Now, I want to talk about in the next slide what's the significance of them being linear with each other. Oh yeah, actually, this is telling you how I know they are linear, all right? Because once again, the exponent is 1 on both of them. All right. Now, what's the significance of that? If the two variables are linear, then any proper experiment that lists these variables means if you graph that data, it would be a proper line, right? Because this shows you a linear relationship. All right. Now, let me give an example of an equation where the two variables are not linear. So let's just say I had a different scientific theory, and that scientific theory says that P and T are related by this instead. All right. P and T are not linear with each other, right? Like for example, I would put my box that I was talking about the y variable and x variable. Suddenly that pesky squared kind of messes things up. All right. So the fact this exponent is not 1 means it's definitely not a linear relationship. All right. This is called a squared relationship is one way you could describe it. All right. And the significance of this is if you did this experiment properly and you graphed it, you would actually not get a line. All right. So that's another indication that it's not linear because you graph it and it's not line. So once again, if you know the equation that relates to the two variables in your experiment, you should be able to tell whether the experimental data will result in a linear graph or not just by looking at the equation. Just by at a glance, you should be able to see that those two variables are linear, right? And thus it should be a linear relationship. So what I'm going to do is show you guys, I'm going to give you guys a bunch of equations. I think there is 8 equations. And your job is to look at V and G. And by looking at V and G in each of these equations, you should be able to see which ones are linear and which ones are not linear. All right. So here is the slide right now. And what I want you to do is go through all 8 of these, 8 because it's 4A and 4B, and see which ones look at V and G and which ones are linear. Right. And then also another thing where you're doing that, you should notice that which one's going to be the y variable, which one's going to be the x variable, knowing this in the form of y equals mx. Right? Okay, why don't you go ahead and take some time to figure that out. So go through each one of these, which ones are linear, which ones are not linear. Okay, let's sort of see what we got. So things I'm looking at right here, I can sort of see a y variable, I can see an x variable right there, and I'm looking at them, do they both have an exponent of 1? Hopefully you can sort of see that, yes, this one is definitely linear. All right. Versus when you look at this one, you look at your y variable and x variable, is it pretty clear that's not linear because of the pesky square root? All right, so that one's definitely a no. All right. So when you go into 3, hopefully you can sort of see this squared also messes things up here, so this is not linear either. All right, so these are no. 4A is a tricky one. All right, anytime you see a letter in the denominator means it is not linear. So a lot of people look at this and think, oh, well, that exponent is 1. Actually, if you want to be technical about it, the fact that it's in the denominator means that exponent is officially -1. So that is not linear. This is actually called an inverse relationship. So this is actually a no. And the reason I wrote 4b here is because see the difference with 4b? 4b is definitely a yes. So in other words, that g being in the numerator versus the denominator is actually really important. Anytime the g is in the denominator, not linear. That's an inverse relationship. V and g both in numerator, good to go. All right. 5, 6, and 7, what I want to point out for these, sometimes there's multiple letters. And what I want you to sort of focus on is just V and G. So in other words, yes, there could be other letters in this equation, but to answer whether V and G are linear, you need to focus attention only on V and G. So you look at V and G here. Okay, hopefully you can see clearly, yes, that is linear, right? But a lot of people sometimes get confused with this number 6 because you see the squared right here. But notice that squared is acting on the A. And if you look at V and G alone, like this, hopefully you can sort of see, oh, V and G do appear to be linear with each other. Now, if I were to ask you about V and A are not linear with each other, but V and G definitely are. And so with number 7, V and G are not. V and A happen to be linear, but V and G are not. Okay? All right, so this is the list right here. If you could get all of these right, or if you understand these, then you know how to do this first objective right here, which is determine the y and x variables and determine whether they're linear or not. All right, so actually you don't know how to do that step right there, but you can do this. Okay. I'm going to skip actually this linearize if they're not linear. That's actually going to be the topic of the second video. All right. So I'm going to skip right to here, determine what the slope represents. All right. So for this one, let me go through a list of equations. So this one's determine what the slope is telling you, determine what the slope represents. So first confirm that all these equations, if you look at P and T, they all represent linear relationships between P and T. So P and T, P and T, P and T, P and T, P and T. Do you all feel like you understand that P and T are linear right here? Hopefully you can clearly see, like I'm going to put a box around like y variable, x variable, right? Whoops, y variable, x variable, and stuff like that, right? And the reason I'm putting that box around there is going to help us with this next step about determining the information the slope is telling you, all right? Notice that the slope is the coefficient of the independent variable. What do I mean by coefficient? Coefficient is a fancy mathematical term for what's being multiplied by the independent variable. Independent meaning the x variable. So do you see, once again, this formula that we have for linear formulas? All right. Do you see this x variable right here? Do you see whatever's being multiplied by the x variable is the slope? So this is called a coefficient. Whatever is being multiplied by x is the coefficient of x. And this thing that's being multiplied by x is the slope. So you need to kind of take this pattern to these guys right here. Do you see I see the y variable and the x variable here? So when I'm going to look at this equation right here is look at what's being multiplied by the x variable right here. I'm going to do green circle to represent the slope. You see right there, I can sort of say that here the slope is definitely represented by 3. Whoops, 3. Right here, I could put a circle around that thing that's being multiplied by the x variable and see that the slope here is a. Let me do this next one and see if you guys can do the other 3. So once again, y variable, x variable, looking pretty good, looking nice and linear. And then what I'm looking at is what's being multiplied by the x variable. And that is 5r. Not just 5 and not just r. It's 5r. Everything you see right there This was being multiplied by the x variable, right? All right, so why don't you guys try to see if you can do the last three, right? Why don't you see if you can tell me what the slope represents? Okay, I hope that was enough time to go through all three. So here I'm going to put the boxes on. I'm going to eventually stop doing these boxes, although a lot of people find that as you continue on doing all these labs in the future, still drawing these boxes is actually going to be really, really helpful. So I did that one right there, and hopefully you can see here the slope is a squared, right? I'm not going to draw the box for this last turn. I'm just going to draw the answer. Here the slope is 1/3 g, and this last one the slope is 1/v. All right, so this is this second step, is determining what information the slope is telling you. All right, so that's this right here. Determine what the slope represents. Okay. So hopefully that wasn't too bad. Let's try another one real quick right here so that I can show you kind of from beginning to end what this step actually means in the context of the problem. Like what you're going to do with this meaning right here. Okay. So let's start off with even a new equation right here. Let's just say once again we have P and T as your original data table. So for example, this means you would have collected data and P and T are two variables. One thing I see right away, right now, just by looking at that equation, y variable, x variable, right? So P is definitely my y variable, T is definitely my x variable. Another thing I can see right away is that they are definitely linear, right? I'm going to write down this list, in fact, right? I'm going to say the y variable is definitely P, the x variable is definitely T. And the last thing I know is that the slope for sure is, in this case, hopefully you guys have already thought of it in your head. So this slope for sure is the square root of A. Right? And the other thing I noticed is that P and T are linear. Right? Okay. So if you can do that, let me show you what this means in the context of a lab, what you're going to be doing. So like I said, say you're here and you would have collected P and T data right here. All right, so you had a bunch of numbers all in these squares right here. And then once again, the lab equation that which you would have written down separately is right there. Okay, so things I can see right away. Y variable, X variable, slope. I was going to color code it. Slope. Right? So what does that mean? That means I know that all these p-values right here that are in this part of the table, all those p-values right there, those are going to be my y variables. Oh, why did the pen thickness change? Let me see if I can change it up. Okay, so all those are going to be my p variables, and all my t's are going to be my x variables. Okay, I will title this, and I'm going to go over some of these details in terms of the titles and stuff like that. All right, you're going to graph it, and then because they are linear, right, I should roughly get a line, all right, if I do things properly. Okay, and then next thing I'm going to do is do a line of best fit, drawing it with a straight edge. All right. And then I'm going to find the slope of that line by choosing 2 points on that line. So I'm going to find 2 points on the line. I'm going to look for places where it crosses the grid. So I don't know, maybe that dot right there crosses the grid. Looks like that grid point right there crosses the grid. So I'm going to do my slope calculation and calculate that slope. All right. So I'm going to have like this minus that all over this minus that, like changing y over changing x. all right, and get a number right here. So I'm just going to make up a number. Let's just say I calculate that slope between these 2 points right here. Let's just pretend I got 5. All right, so let's just pretend that slope is 5. So I'm going to write that right here. I got a slope of 5 right here. So I'm going to write that again right here. Next down here, what do I write for slope being a variable? That comes from this equation up here that I already did up here, right? So see this equation right here? I already knew the slope was root A. So I'm going to write the slope here as root A. Now, this next step is actually a very important piece of logic. Notice that I know the slope is 5, and I know the slope is root A. So I got the slope being 5 from my graph. I got the slope being root A from my equation. Now, if the slope is 5 and the slope is also root A, well, if they're both equal to the slope, the only thing I conclude is that these two things are also equal to each other, right? Because they both are the slope. Hopefully that logic makes sense, right? Because if they're both equal to the slope, that means they've got to be equal to each other, which means I can set up an equation here that says that root A equals 5, and then I can use that information to solve for A. So this is what you're going to be doing for every lab. And this step I just did right here is what I mean by this. Use the slope to find the experimental value of the variable the slope represents. So that's always going to be the very last step. Unless I ask you to do some extra steps, which we'll talk about later, specific to the lab. But this is all universally one of the final steps in doing a lab analysis is by setting the value of the slope equal to what the variable of the slope was supposed to be, right? This comes from your graph. This comes from your equation. Set them equal to each other and solve, right? So let me give another example. It's going to, once again, pretend it's the same P and T, but I'm going to pretend, let's just say the equation was a different equation. Say the equation was this. T over V, okay? This one can be a little bit confusing. All right, if you look at, I'm going to put a box on the y variable, x variable again, and that once again is still nice and linear. All right, some people still get confused by the slope, so sometimes it helps some people. If I wrote this out like this is actually the exact same thing. All right, and then so now if I put my box on the x variable right there, it's much easier to see for a lot of people what the slope is right there. Right. So even knowing that right away, I can actually jump all the way down here. Not sure if I all the way down there, right? One over V, right? Because I got that from equation, right? And in the meantime, I already know that I'll graph the P variable here as the Y variable, the T stuff right here. So I'll grab that from a data table and plot those points. Line of best fit. I find the slope of that line. Finding 2 points, 2 proper points right here. So I'll show that calculation that I do right here to find that slope calculation. So let's say I do that slope calculation, change the y over changing x. Oh, it's maybe do that. Okay, right? And then let's just say I get the number 5 right here for that slope. Let's just pretend I just made that up. All right. So then, of course, then down right here, if 5 is the slope, right, and 1 over v is the slope, I can then set those two things equal to each other and solve for v. So in other words, the entire point of this lab was to actually, like the entire point of me collecting P and T data was to actually eventually use the slope to find the letter of the value of this letter right in here, right? Or like for this lab, the whole purpose of me getting P and T was to find through the slope eventually the value of this letter right here. All right, so let me summarize the general steps for data analysis. These are the general steps up here. Okay. And in the meantime, I'll give some more details about each of these steps too as well. So when you would linearize the data, I already mentioned This would be true if the equation wasn't linear, and I never covered that in this lesson. This will be covered in the next video. All right, but next you have to graph the data. All right, some details about graphing the data they didn't talk about, so I'm going to talk about it a little bit more detail right now. The title of that graph is always going to be the y variable versus the x variable. So, and I don't necessarily literally mean like the words y variable, x variable. Notice right here, it's what the y variable, x variable were in the equation, right? Or with your data. So like, for example, right here, I'll still do P versus T. All right, so it's always y variable versus x variable, right? Next, notice that you have to label the axes correctly with both variable and units. So do you see these titles right here? Here I wrote the variables. One thing I'm missing is the units of those variables in here. So I should need to have units of those variables in there. Now, I don't know what the units of these variables are because I kind of made up this whole equation. I don't even know what P and T are supposed to represent. But in the labs you guys do, you would know actually what each variable represents and what those units are. Like presumably T, most commonly T is used to represent time. So the most common units of time we have is seconds. So we probably put seconds there. Okay, so we have the variable and its units. Variable and its units, all right? Make sure your scale starts from 0 on both axes. So you want to choose a proper scale when you're plotting these dots. All right. And make sure it starts from 0, right? What do I mean by that? It's sort of like the way you kind of choose a scale is sort of like thinking about like, okay, what's the biggest number that you're going to plot? Well, I kind of say on the t axis, I'm going to look at all these numbers right here and look at the biggest number that's here, right? And thus that might tell me what the highest number here is going to be. Okay. Now you don't have to choose the highest number here and put it right there. I mean, and it's like, for example, if these numbers like go all the way up to like 4.6, you don't necessarily have to make that 4.6. In fact, you probably don't want to do that because one of the things you want to do is maybe choose. So maybe you want to choose a number that's going to divide evenly so that each one of these little segments right here is an even, nice, like clean number. Maybe a decimal, but a nice, super clean number. Like 4.6, so it even tells you right here, this grid is 30 things wide. If I do 4.6 divided by 30, I can sort of see that's not going to be a nice even decimal. So for example, if I do 4.8 divided by 30, that actually might be better. Or even 6 divided by 30. 6 divided by 30, a nice clean number. Let me check to see. All right, so I'm going to take my calculator and do 4.8 divided by 30. 4.8 divided by 30 is 0.16. So each one of these will represent 0.16. Or I could do 6 divided by 30, and each variable is 0.2. Heck, I don't know. That's a nice even one. I'll do 6 divided by 30. So I'm going to make that one 6. All right. And then what that means is that starting from 0, each one of these goes up by 0.2. All right. So 0.2, 0.4, 0.6, 0.8, 1. 1, 2, 3, 4, 5, 2. And so on and so forth. All right. And you can kind of fill out the rest. 3, 4, 5, 6. Right? And then you're going to do the same thing for the p-scale, right? And you need to make sure they both start at 0 going up. Right? So that's kind of really important here. But start scale. Oh yeah, and that the last one is choose a scale that's appropriate for the entire data. That's what I was just kind of talking about. Right? So an inappropriate one would be to use 12 up here. Why would it be inappropriate to use 12? Well, if your numbers only go to 4.6, you're not even going to go halfway, right? And that would be kind of a waste of graph space. And you want to make sure you try to use as much of the graph as possible. All right. So that's graphing. Next step, draw a line of best fit. Use a straight edge. I use my straight line tool right here. Use a straight edge. Now, what you're looking for is just kind of eyeballing a line that works well, which seems sort of like hand wavy. a little bit, but just do your best. Now, it's not a connect the dot thing, so do not try to connect those dots, right? Some of them are going to be off. That's totally fine, all right? In fact, the entire purpose of this line of best fit is that, remember, each of these data points has random error, right? So they're not supposed to be perfect. How do we get rid of random error is through this line of best fit, because we can sort of imagine these data points were probably a little bit off, but what they overall represented, this red line is supposed to represent maybe the true data. All right. So it's a way to get rid of random error. So don't try to connect the dots, just kind of go sort of through. Now, there is an official technique to find an official line of best fit. Don't worry about that. You're just going to eyeball it. And the next thing I want you to do not force it to go through 0, 0. All right. So if it doesn't naturally go through 0, 0, don't make it. All right. So if it might be like that or like that, all right, just let the dots that you plotted be your guide. Okay. Next, you're going to find the slope of the line of best fit. Remember how many points it requires to find the slope of a line? 2 points. You always need to show which 2 points you chose to find the slope of a line. Okay? And what you're looking for, once again, do not use data points, because those data points have random error in them. So they're not really valid representations of what your overall data was showing. So you are looking for grid points that line goes through. So hopefully you can find somewhere in this line some sort of grid point that it goes through one point and some sort of grid point it goes through another point. Try not to use 0, 0. That seems kind of like try to find 2 grid points that it goes through. All right. Oops, where were we? Here. Show what points you use to calculate slope and look for places where the line crosses the grid points right here. So show what points. How do you show it? Either by some people like to circle it on the graph like I kind of did right here. Some people like to show what points they use right here. So like X, Y, Y, X, X, something like that, right? So I can kind of see which values you used. Whatever the case is, I need to see what points you used and how you calculated the slope, all right? And the last step is to do this thing that I've been showing you right here, where if you know what the slope represents from the equation and you know what the value of the slope is, you set them equal to each other and you solve for that letter, right? So that's that last step right here. Set the slope value and from the graph and the slope equation from your equation, right? The slope variable from the equation, and set them equal to each other and solve. Right? Showing the algebra, need to solve for this variable. Like right here, I kind of showed the algebra. Cool, there's only one step. Here, you're going to show your algebra right here. And then make sure you report these units right here. Okay, so always report what units this variable is. All right, that's all for video 1 of this.